working with probability. Remember, one way of assigning probability is to do the classical approach, where we can find the number of ways the event we're interested in can happen, divided by the total number of items in our sample space, and that ratio would give us the probability of that event, the likelihood that it would occur. Now, we were doing this in an example in a video that I've linked in the description of this video. So if you want to review the idea of the basic properties of probability, I invite you to go back and watch that one as well. When we were looking at the probabilities in that particular video, the sample spaces were relatively small. So it was no big deal to use either a tree diagram to list out the elements in the sample space, or to actually just list them out from looking at what could occur and then physically finding out the ones that meet our requirement, and then physically counting how many met our requirement for our event, divided by how many were in the sample space. But what if we have a situation that is way too big of a sample space for us to take the time to actually list it out and keep track of all of the different things, as well as then physically count how many meet the requirement of our event, divided by how many are totally in the sample space? Well, that's where counting techniques come in, and a place where counting techniques are very helpful. So with counting techniques, I'm actually just jumping to how many ways can this thing occur, instead of actually listing out the things that meet the requirement and counting them. And so it's very beneficial when we go back to the idea of finding our probabilities. But to do this, we need to get just some introductory counting techniques under our belt. And we are going to work with the counting techniques of the multiplication rule of counting, combinations, permutations, permutations with non-distinct items, and then compound counting techniques to get the foundation we particularly need in an introductory statistics course. If you wanted to look at further counting techniques, then you would need to look at different videos that would be with combinatorics. But let's get started on the counting techniques that we are going to cover. So the first one is the multiplication rule of counting. So with the multiplication rule of counting, you want to think if there's some sort of sequence of choices that I'm going to make, or if I'm able to reuse items in the next phase of the choice, even if I've used it before, and if there are n1 ways the first choice can be made, n sub 2 ways the second choice can be made, the third choice n sub 3 ways, etc., then the number of ways that you can take choice 1 followed by choice 2 followed by choice 3 followed by choice 4, etc., will be n sub 1 times n sub 2 times n sub 3. So they call this the multiplication rule of counting because you're multiplying the number of ways each event can happen individually to get the total number of ways of that sequencing. So here are some examples of counting techniques that we can use our multiplication rule of counting in. So the first one says how many different pins can be formed if the pin is 4 digits long. So this is like when you're trying to open up your smartphone and you have to put in a 4-digit pin, or when you're looking at a bank card that you need a 4-digit pin, or whichever case that is. So when you think about this and it doesn't tell you at all any conditions about whether you can reuse a number or anything like that, then you assume that you can use that number in this particular setting. If it is a setting where you know that that's the way that it occurs, that you can't reuse a number, then you want to just kind of think about your everyday life situation with those occurrences. But with pins, I can use the same digit, and there's no requirement that I can't use any digit. Now, what's a digit? A digit is either your 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So there are 10 digits to choose from in each slot of your 4-digit pin. So when I think about this, I'm going to choose my digit for my first slot in my 4-digit pin, and then I'm going to choose my number in my second slot for my 4-digit pin, and then the third slot for the 4-digit pin, and then the fourth slot for the 4-digit pin. So this is like when you set up your pin to start with. Well, you have 10 digits to choose from for your first digit choice, right? The 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And you have 10 digits still for the second choice, and for the third choice, and for the fourth choice. So when you multiply 10 times 10 times 10 times 10, you get 10 to the fourth, or 10,000. So there are 10,000 different ways that you could choose a 4-digit pin. Let's look at the next thing. How many different license plates can be made if the plates are 2 digits followed by 3 letters, and a plate cannot start with 0? So I'm going to just make blanks for where I have my slots that I'm going to then put in the number of choices I have at that stage of the sequencing of my events that I go through. So I'm going to place my first digit, then my second digit, then my first letter, my second letter, and my third letter. And now I'm going to put in the number of ways I have to select from for each of those choices. So it's 2 digits, followed by 3 letters, and my plate cannot start with 0. So when I'm not going to be able to use 0 for my first digit choice, that leaves me just 9 digits to pick from for the first choice slot. And then how many different ways can you choose the digit for the second slot? Well, it doesn't say I can't use 0 this time. So now there's 10 choices for that second slot. Now I'm at a letter. There are 26 letters in the alphabet. So I have 26 choices for the first letter, 26 choices for the second letter, and 26 choices for the third letter. And when you multiply all those together, you get 1,581,840. So this is why we can have just those slots for the license plates, and we still have plenty of numbers, letter sequences like this to assign for the automobiles. Okay, then the next one. How many different outfit choices are there if you are choosing from 4 shirts, 3 jeans, and 5 pairs of shoes? Well, your outfit choice is going to be pick a shirt, pick a pair of jeans, pick a pair of shoes. You have 4 shirts to choose from, so that's 4 times. You have 3 pairs of jeans to pick from, and then times you have 5 pairs of shoes. And then when you multiply, 4 times 3 is 12, times 5 gives me 60 different outfit choices. So this gives you several different examples of the multiplication rule of counting. Next up, we are going to look at permutations and combinations. The next type of counting techniques that we're going to talk about are where you have a fixed set of items that are distinct items, and there are n of those items in the set, and you are going to select r items out of that group. So this is different than the rule of counting, that we are actually talking about a closed set of distinct items instead of a sequence of my different events that I'm pulling from. Also with this, there's 2 different situations. So first, if we're looking at permutations, you have n items in this set, and you're pulling r out of those n items. So r has to be less than or equal to n. And in those r items that you pick, you're going to keep track of the order in the set and count it a different count as you go through keeping track of the order. So a lot of times we say order is important or order matters. That's a permutation. So it says let n be the number of distinct items of which r items are being selected, and repetition is not allowed. The number of ordered arrangements, so you're keeping track of the order, is denoted by capital P for, in this case, the first letter of permutation, and it has the subscripts of n, then R, either on either side of your capital P or after your capital P with a comma between them. But N is the total number in your group. R is the number you're selecting out of that group. And with permutations, it's when you have a situation where your order would matter. If the formula is given to you by the permutations N choose R is equal to N factorial over N minus R factorial. Now when we're looking at this formula and I want to use the factorial notation, N factorial means to take that number and multiply it by all the natural numbers below it. So for example, 5 factorial would be 5 times 4 times 3 times 2 times 1. 1 factorial would just be 1. And by definition, you just have to have the definition that 0 factorial is equal to 1. Now that's what the factorial is. So I have n factorial in the numerator divided by, in parentheses, n minus r factorial. Now you can either do this by formula that is listed here, and we'll show some examples of that, or there is a place on your calculator that will do the work for the permutations. So with the TI-83 or TI-84 calculator, and you want to do a permutation, you put in the number for the n first on your calculating screen. Then you'll push the math button. You'll cursor right to PRB choice, and then in there select NPR, push enter, and then put in your R number and push enter, and it will do this formula for you and give out the value, and you wouldn't have to then do the expansion with your factorial notation. And I'll talk about that when we get to an example. The next is combinations. And with combinations, it says let n be the number of distinct items of which R items are being selected, and repetition is not allowed. So it sounds just like permutations when you get started. The key here is that it's the number of selections of R items from N items without order being important. So ordering within the group is not important for combinations, but it was important for permutations. The symbolism for combinations, well, combination starts with a C, so it'll be NCR, or C with an N comma R, or an elongated parenthesis with an N in the top and an R in the bottom, but no fraction bar in between. Now that last notation really isn't used very often anymore. It was very common several years back, but now they've pretty much gone with the notation where you have the N, then the C, then the R for combinations. Now the formula for combinations looks very similar to for permutations, except they have to divide out the order. So it's n factorial in the numerator, then your fraction bar, and then you do have an n minus r in parentheses factorial in the denominator with an r factorial also in the denominator, and that's how the ordering gets divided out so that you're not accounting for the order. So let's look at these examples. One of the things you want to remember is that a lot of times when you're doing these counting techniques, they've just come after some introductory work with probability and might return to probability again. But in any case, they're pretty much in the same unit of material with each other in a lot of circumstances. So you need to really make sure you know when they're asking you to form a probability, which is the ratio of the number of ways your event can happen divided by the number of possible ways in your sample space, or when they're asking you to find how many ways something can happen, in which case you're going to answer with numbers that many times are way bigger than 1. Remember, probabilities are 0 to 1 inclusive, and counting is usually huge numbers that we get for our answers, or bigger numbers. So here, what you look for in the question, it says how many different. See, if it wanted the probability, it would say, what's the probability that? But here it says, how many different ways can something happen? It's a counting question. Now, can a 15-member club choose a president, vice president, secretary, and treasurer? So you're talking about that club of 15 members being that kind of closed group. And also you're looking at 4 different items that you're selecting out of that 15-member club: a president, a vice president, a secretary, a treasurer. You're not going to have any repetition allowed because you're not going to have a member take 2 different offices. It's somebody is specifically for the president, somebody else for the vice president, a different person for the secretary, and then another person for the treasurer. So this all has that aspect of either a permutation combination, but not a multiplication rule of counting. Now, how do I know which it is between permutation and combination? Well, it matters who's the president and who's the vice president and who's the secretary and who's the treasurer. I'm sure it matters to the people themselves, and it also matters in how the club functions by who sits in each of those offices. So since the placement within these matters, order matters within the selection, so that makes it a permutation. So this first one is permutations. There are totally 15 members in the club, and I am picking 1, 2, 3, 4 of them. So if I look at it by my calculator, I would put in the 15 and then push the math key and then cursor over to prob, and then I cursor down to NPR, and then hit the 4 and enter. And when I do that, I'll see 32,760. 32,760 different ways that can happen. Now, if I do the formula for it, my permutations of 15 taken 4 at a time is n factorial, so 15 factorial over, in parentheses, n 15 minus r 4 factorial. Remember, order of operations, you do what's inside parentheses first. So that's 15 factorial over 11 factorial. And then a way to work with these a little bit more concisely instead of getting really, really big numbers is you want to write out the multiplication in the sequence down until you hit the largest of the factorials in the other part of the fraction. So 15 factorial I'll write as 15 times 14 times 13 times 12 times 11 factorial. 11 factorial means 11 times 10 times 9 times 8 times 7, etc. But I'm leaving that as 11 factorial because I noticed there's also 11 factorial in the denominator. So it would be your 11 times 10 times 9 times 8 times 7, etc. So they are common factor pairs all the way down the line between the denominator and the numerator. And then I can just multiply the 15 times the 14 times the 13 times the 12, and I will get that 32,760. Let's look at the next one. How many ways can a 10-runner race finish if the prizes go to runners finishing first, second, and third? Well, again, it's just the runners in the race that you're picking from. Nobody can come in both first and second, so there's no repetition. And order matters. You know, who finishes in that race, everybody's there cheering people on, and who finishes first matters not only to the person, but the finalized results of the race. So I have a permutation setting again. So this is permutations. There were 10 runners, and I'm choosing 1, 2, 3 out of the 10 runners. Order matters, so it's a permutation. And when we run that through either the calculator or through the formula, you'll get that that's 720 different ways. Next up, how many different 5-book selections can be made from a stack of 7 books? Well, here I have my stack of 7 books, and I'm only picking 5 out of the stack. And I'm not going to pick the same book twice, so there's no repetition. But the order in which I pick my books doesn't really matter. I'm going to take them home, and then I'm going to decide, which one I want to read and all that kind of stuff. So order doesn't matter here. So this is a combination. There are 7 total in the group, and you're picking 5 of them. And when I run that through my calculator, I will put the 7, and then I'll go math, prob, down to NCR, pick it, put in the 5, push enter, and you will see 21. And then we could also do this with its formula so that you can see it. Combinations of 7 choose 5 is 7 factorial over, now remember it's r factorial, so 5 factorial times n minus r factorial, so 7 minus 5 factorial. So that gives me 7 factorial over 5 factorial times 2 factorial. Running this 7 factorial down until it hits the largest one, and then the one that remove as common factor pairs with the factorial notation you want to expand out. So that'll be 7 times 6 times 5 factorial over 5 factorial times 2 times 1. The 5 factorials remove. 2 times 1 is 2. So this gives me 42 divided by 2, which again is 21. So that gives you a couple examples of how to tell between combinations and permutations. The last type is permutations with nondistinct items. With permutations of nondistinct items, you have a set of n items, but they're not all different from each other. Some of them are the same as each other, and you want to see how many different arrangements you could make out of this set of n different. Now when we're looking at permutations with non-distinct items, the difference between this and the work with the permutations we already did is that in the permutations with non-distinct items, they are not all different from each other. Some of them within the n items are identical to each other, so you can't tell them apart. So when we look at having it in an ordering situation, you wouldn't be able to tell if those identical things switched places, so you don't want to count that as a separate ordering when it's not distinguishable. Now to do this, what we have to do is take the factorial of the overall number of items that we have, but then divide out those counts of things that we wouldn't be able to identify as different. So we're going to divide by the multiplication of the number of repeated things of one type, factorial, times the number of the second group that are identical to each other, that number factorial, times all the way down until we've identified each of those repeating groups. And the other thing that's different about these than with the other permutations is in the other permutations we were picking so many out of the group, and sometimes we use the whole group, but we could use a smaller number than the whole group. Remember, r could be less than or equal to n. But in the permutations with non-distinct items, you're always taking the entire set of the n items and looking at the different recognizable arrangements of those. So let's see an example of this type. So here, because it's easy to see when we have letters that we're using, we're going to use an example of where it asks us how many different words, and words is in quotes. So they don't mean actual words that you can look up in the dictionary. They're just talking about different arrangements of the letters that are recognizable from the others, can be formed from the letters of the word success. Okay, so I want to see how many different, recognizably different arrangements I can make from the letters of the word success. Well, this is where there's repeated elements. There's 2 C's, there's 3 S's, and total amount of letters 1, 2, 3, 4, 5, 6, 7. So this will be 7 factorial divided by, now my S's, there are 1, 2, 3 of them, so that's 3 factorial. And then there's only 1 U, so I don't need to put 1 factorial. 1 factorial is just 1, and when I multiply by 1, I still have what I had before, so I don't need to put that in. It doesn't serve us any purpose. And then there are 2 C's, so I'll have 2 factorial, and there's only 1 E, so again, I could put the 1 factorial in there, but it doesn't affect what my answer is going to come out as. So now when I get that factorial, and if I had other repeating letters in there, I keep going with all of the factorials multiplied of the letters that repeat. And when I work through this, I see 3 factorial is my bigger one. So I have 7 times 6 times 5 times 4 times 3 factorial. And then divided by 3 factorial times, and 2 factorial, I'll multiply that out as 2 times 1. The common factor pairs of the 3 factorials, they both encompass 3 times 2 times 1, so I can bring them out as a common factor pair altogether. Then I have a common factor of 2 that goes into 4 twice. And then when I look at the multiplication here, I have 7 times 6 times 5 times 2. Well, 5 times 2 is 10. 10 times 42 is 420. So that gives me 420 different, recognizably different letter arrangements of the letters of the word success.